Imagine this. You pull into a charging station, plug in your electric car, and walk inside to grab a coffee. And before you even finish paying, your battery's almost full. No waiting around, no checking your phone every 2 minutes, and no wondering if you'll actually make it home. For years, engineers have promised this future, a future where electric cars could charge almost as quickly as filling a tank with fuel. But there was one problem. They couldn't build the battery, not outside the laboratory and not inside real cars. Until now, because Stellantis, the company behind Dodge, Jeep, Chrysler, Maserati, and other several brands, has just done something that could change the entire EV industry. They have put a solid state battery inside a real Dodge Charger and start driving it on public roads. Not a concept car, not a computer simulation, a real car on real roads. And if these tests work, this could become one of the biggest breakthroughs in the automotive industry for decades. Let's see how. But here's what most people don't realize. Every electric car today is making a compromise. Whether it's a Tesla, BMW, Hyundai, or a Porsche, they're all essentially using the same lithium-ion battery technology. And while it's impressive, it's also holding the industry back. Because inside every lithium-ion battery, there's a liquid called an electrolyte. Think of it as a motorway. Lithium ions race back and forth along that motorway every time you charge or drive. Without it, the battery is just an expensive box. But here's the problem, liquids aren't perfect. They can heat up, they can be flammable, and they can limit how quickly you can push energy into a battery. And which means engineers have to add cooling systems, protective structures, and extra safety equipment. All of that adds weight. And when you're building a performance car, weight is the enemy. So, engineers started asking one simple question. What if we got rid of the liquid completely? And that became known as the solid state battery. And on paper, it looked revolutionary. A solid state battery changes one fundamental component. The liquid becomes solid. Sounds simple, isn't it? But if it works, the benefits are enormous. Imagine carrying two backpacks. They both weigh exactly the same, but one can carry 50% more. Which one would you choose? That's essentially what engineers are trying to achieve. Factorial's best battery cells have demonstrated an energy density of around 375 watt hour per kilogram, while many of today's EV batteries operate between 200 and 300 watt hour per kilogram. That means more driving range, less battery weight, better efficiency, and better performance. And for a car like the Dodge Charger Daytona, less weight means better acceleration, better handling, and better efficiency. Now let's talk about almost every EV car owner complains about charging. Because no matter how good the car is, nobody enjoys waiting. Imagine pouring water into a glass. Pour too slowly and it takes forever. Pour too quickly and it spills everywhere. Batteries behave in a surprisingly similar way. Push too much energy into them and then generate heat. Push too much heat into them and it damages the battery. So charging quickly isn't simply just adding more electricity. It's about controlling the heat. And that's where factorial technology becomes interesting. Their fast cells can reportedly charge from 15% to 19% in just 18 minutes. That's the kind of number engineers have been chasing for years. There's one topic every EV company would rather avoid: battery fires. Now they're actually quite rare, but engineers don't design for what's likely. They design for what could happen. One of the biggest risks is something called thermal runaway. Imagine one domino falling, then another, until the whole chain collapses. That's essentially what happens inside a failing battery. Heat creates more heat, which creates even more heat. A solid electrolyte contains far less flammable materials, significantly reducing that risk. No wonder nearly every major automaker is investing billions into this technology. Here's the twist. Science was never the biggest problem, the engineering was. Because batteries don't live inside perfect laboratories. Because cars can hit potholes, they vibrate, They sit inside traffic and extreme heat. They drive into freezing winters. They fast charge. They discharge over and over again. Imagine asking your phone battery to survive that. Exactly. That's why so many solid state batteries got stuck. Engineers struggle with cracking materials, manufacturing complexity, poor durability, limited life cycles, and scaling production. Making one battery is difficult. Making millions is an entire different challenge. That's why solid state batteries have been described as 5 years away, again, and again. But Factorial and Stellantis appear to have crossed the important milestone. They validated automotive-sized battery cells, they demonstrated rapid charging, and then they put them inside a real car. This is where everything changes. This isn't just another flashy prototype. This isn't just another press release. This is real engineering. Stellantis has integrated Factorial's battery into a Dodge Charger Daytona development vehicle and started driving it. Now the real questions begin. Can it survive thousands of kilometers? Can it handle repeated fast charging? Can it handle deep weather stress? Can it perform after years of use? Only roads can answer these questions. Stellantis even redesigned parts for the battery pack and control systems to integrate these fast cells safely. This is where battery science becomes automotive engineering, and here's why it matters so much. This isn't just Dodge. If this technology succeeds, it could eventually be spread across millions of vehicles built on Stellantis STLA large platforms. Imagine electric vehicles with over 800 kilometers of range, lighter battery packs, faster charging, improved safety, and lower costs over time. That's the vision. But here's something that makes the story even more interesting. This isn't just about one company building a better battery. It's about the entire industry competing to solve the same engineering problem in different ways. Take General Motors. Rather than waiting for solid-state battery to mature, GM is investing heavily into silicon-anode battery technology. Why? Because from a business perspective, the best technology isn't the one that wins. Sometimes it's the one that reaches the customers first. Silicon-anode batteries can use of today's existing lithium-ion manufacturing infrastructure, making them easier to scale. GM believes that this technology could increase EV range from roughly 310 miles to as much as 574 miles, while reaching the market years sooner than many solid-state batteries. And that's what I find interesting. The battery industry isn't just following one roadmap, it's becoming an engineering race. One company is getting better on solid-state, another is getting better on silicon anodes. Others are investing in sodium-ion batteries, and they're all chasing for the same goal: longer range, faster charging, lower cost, and better safety. But they're taking completely different routes to get there. And that's exactly what makes engineering so exciting. There isn't always just one perfect solution. Different teams study the same problem, apply different scientific principles, work within different manufacturing constraints, and sometimes arrive at completely different answers. As someone who's passionate about engineering, that's one of the biggest reasons I want to make this video. It's not about the batteries, it's about how material science, mechanical engineering, electrical engineering, chemical engineering, manufacturing engineering, and business strategy all come together to solve real-world problems. Every new battery isn't just simply a scientific breakthrough. It's a result of thousands of engineering decisions, trade-offs, simulations, prototypes, and years of testing. And that's what makes the industry so exciting. Whether it's solid-state batteries, which becomes the future, or silicon anode technology, which becomes the future. One thing is certain: the next generation of electric vehicles will be defined by the engineering. For years, solid-state batteries have lived in research papers, conference presentations, laboratories, and headlines that have always ended with "coming soon." But today is different. For the first time, this technology isn't sitting on a laboratory bench, it's rolling on public roads. Will it succeed? Nobody knows. Engineering has a habit of surprising us. But one thing is certain: the race to build the next generation of batteries has officially left the lab. And now, the real test begins. If you enjoyed breaking down the engineering behind technologies shaping the future of transportation, subscribe to me and join me as we explore innovations driving the next generation of automotive engineering. Thank you so much.